Good morning. We're going to start with a continuation of the topic of mathematical derivation in physics, then go on to other topics. This is again an extremely long, overlong lecture, but it's the last such one. The next two on philosophy, I know how to condense. And this time, for a briefer indication of the role of math in physics, we're going to look at the work of James Clerk Maxwell. Even though it's spelled C-L-E-R-K, I've been informed by Donna Monteza that it's pronounced Clark. So I apologize to him, and I'm going to stick with the initials JCM. He is to the field of electromagnetism, in essence, what Newton is to the field of classical mechanics. The JCM, like Newton, comes at the end of a long development and states the fundamental laws underlying all the earlier step-by-step discoveries. In essence, what JCM offers is one force equation and four immortal field equations, on the basis of which one can calculate the electromagnetic force on any charge at any point in space. And once one knows this force, then, using also Newton's laws, one can predict and understand the behavior of all charges, including electric currents and magnets, anywhere and everywhere. Now, a quote from Dave, quote, JCM's equations and Newton's laws of motion form a complete theory of how charges interact and move, just as Newton's theory described how masses interact and move, unquote. JCM's equations are a summary of the basic experimental discoveries in electromagnetism made before him, along with one new and crucial discovery of his own. His equations clearly and concisely wrap up all these discoveries as no one ever had before, and in several cases state the discovery in more general terms and or correct a defect in its earlier formulation. Now, in regard to his new and crucial discovery, which I want to look at first, it is most easily understood in relation to the Faraday experiment we did last time. You remember the experiment showing that a changing magnetic field through an area, for example, the moving magnet through the coil, leads to an electric field or current circulating, going around the coil at right angles. Well, JCM discovered that the causality here was, in a sense, a two-way street. Not only does a changing magnetic field lead to an electric field at right angles, but, and here is his discovery, a changing electric field leads to a magnetic field at right angles. Now, you can think here, to visualize it, of a wire circuit where the wire terminates in two plates a few inches apart, one thereby being charged positively by the current flowing, the other negatively. Well, there is then an electric field going from the positive to the negative plate here. Now place a magnetic compass outside the electric field. Not outside the wire now, but outside the field between the plates. And you will find it orienting itself just as it does around a current-carrying wire. You know, a current-carrying wire has a magnetic field going around it, and now the electric field itself has a magnetic field going around it. Now, this does not happen when the electric field between the plates is steady, only when it gets stronger or weaker. In other words, only when it changes. You see the parallel to the other experiment. So we have this situation. Putting the two experiments together, a changing magnetic field leads to an electric field. That's Faraday's discovery. And a changing electric field leads to a magnetic field. That's JCM's discovery. Now, this dual phenomenon will lead to enormous implications soon. But first I want to look at how did JCM discover his part of it. Now you might think, well, maybe he had some ingenious experiment, such as Faraday did to establish his particle. And the answer is no. Only after he had discovered it did anyone think to try out the kind of experiment I just described with the two plates and the magnet outside it. In fact, JCM reached his discovery by two methods. One involved a very ingenious physical model of the ether, which I personally happen to really like and understand, even though JCM discarded it as flawed. But the other method of reaching this conclusion was a purely mathematical derivation. And given our interest today, regretfully, I'm going to neglect the role of the model and concentrate only on the role of the math here. Physics today, by the way, physicists commonly ignore the model, to their detriment in my opinion, and prove JCM's discovery purely by mathematical means. Now let me indicate to you, at least in pattern, how, using math alone, and remember our topic is how to get to new inductions using math. How, using math alone, JCM deduces his crucial discovery. Let's call it for short that an electric field under certain conditions leads to a magnetic field. I can't give you the steps of the math here, but what it amounts to is this. In the case of one of JCM's original master equations, he performed a legitimate mathematical operation on both sides of the equation. And of course, as you know, and as we've seen earlier, since the two sides of an equation are specified to be equal in quantity, that's what the equal side means, anything you can do legitimately to one side, you should be able to do to the other side without affecting the equality. For example, if the equation in simple terms were A equals B, then I can add 6 to each side and still have an equality, or divide both by y, or take the square root of both, etc., while still ending up with the two sides being equal. But it turned out that when JCM took one of his basic equations and performed a certain complex but legitimate operation on both sides, he reached an impossible result. One side became 0 after the operation, while the other side did not. So his result was 0 equals non-zero, which is a total contradiction. Now he's working here purely in mathematical terms. So he decided at this point, without reference to physics or physical reality, he went back and figured out, with the help of other of his equations, what specific term he would have to add to one side of this original equation so that he wouldn't reach this contradiction. And that term, which was introduced purely by the needs of the math, was then given the standard physical interpretation that would be entailed by the kind of interpretations that were given to all the other terms in the equation. And that new term meant unavoidably that a changing electrical field leads to a magnetic field. So through math alone, he deduced a crucial type of relation between electricity and magnetism, an inductive relation, a generalization that none of the previous experimenters had imagined. A fascinating use of math. Now, since JCM's equations are actually statements of the basic discoveries in the field that were made earlier by such giants as Ampere, Faraday, and others, what JCM really did here was to identify an utterly unsuspected implication of the work of these earlier experimenters. And what made it possible for him to grasp this new implication, you see, just as in the case of Newton with the ISL, it was math that pulled out the unsuspected implication. Just like Newton's math showing us the astonishing fact that the ISL of gravity is implicit in Galileo's observations and Kepler's third law, and yet neither of them could have dreamt of it. In both cases, I hope you see now, Newton and Maxwell, a chain of complex math is necessary to pull out the implications of experimental results and thereby to validate higher level gens which are otherwise unreachable and unprovable. Now let us look at a crucial consequence of what we've already said. And I've been on the verge of making this point for about 10 minutes. Faraday, we said, showed us that a change in the magnetic field, such as one getting weaker and stronger continuously, leads to an electric field, which, while it changes, as JCM has now demonstrated, leads to a magnetic field, which, and etc. To put it another way, and to leave out all the necessary qualifications, a changing electric field leads to a changing magnetic field, which leads to a changing electric field, etc. So what do we have here? Deduced by math, a periodic pulse or oscillation of electric and magnetic fields. The changing electric field going up and then down as the changing magnetic field goes up and then down, which makes another electric field go up and then down, and so on. Now, what does this make you think of? The undulating movement of my hand as I trace out on a graph. You know what Latin for where the undulating comes from? Well, it should make you think of waves. Water waves, for example, where the water goes up and then down, which pushes the adjacent water up and then down. Well, here we have the same thing, a wave, but of course not a water wave. A good name for it would be an electromagnetic wave, since that's its component. The existence of such waves was first predicted and demonstrated, not by experiment, but by JCM's math. I'm leaving aside here the model, which he also used. By math alone, JCM predicted the existence of electromagnetic waves, a phenomenon no one had suspected before. And not only did he predict the existence of the waves by math, but each of their essential characteristics, all of it flowing mathematically from the premises he, along with Newton, had established at the outset. All this led him to a complex wave equation that electromagnetic oscillations or waves have to obey. And therefore he was able to get out of his math the speed of the wave's propagation through space and the laws governing their reflection, refraction, interference, and still other features too complex for us to discuss here. And by the way, all of these purely mathematical deductions were borne out by later experimenters, such as you may have heard of the famous experiments by Hertz, who set out to demonstrate experimentally that every feature deduced by Maxwell about these EM waves was actually true. Now, of course, today, we know that there are various kinds of waves, such as radio waves, microwaves, X-rays, etc. JCM did not know about all of these, but what he predicted was the very existence of electromagnetic waves and of a spectrum of them. Now let's pause for a moment on another crucial discovery of JCM, this one pertaining to the speed of these EM waves. I think you will find this point to be very illuminating as far as the philosophy of induction is concerned. Working simply and only with the mathematical implications of his equation, JCM predicted that the speed of these EM waves is a constant. It's always the same, regardless of the strength of the electric and magnetic field involved, and regardless of how they were generated. And he predicted, no experiment, by mathematical deduction, that this constant philosophy, believe it or not, is, guess what, astounding number? 186,000 miles per second. the very speed which had long been known to be the speed of light. So here is a feat of mathematics truly unbelievable in its proportions. And that's why I climaxed our discussion of the mathematical derivation with this point. Because JCM is now in a position to say, if EM waves have A, B, C, D characteristics pertaining to reflection, refraction, interference, and so on, and including a speed of 186,000 miles a second, and we know that all those characteristics are exactly the characteristics that light and only light has long been known to have, then you cannot escape what conclusion? Light itself is an electromagnetic wave. In other words, by mathematical inference from the equations of electromagnetism, equations based on experiments which in no way involve any study of light, JCM deduces all the known characteristics of light and thereby identifies and proves its essential nature. This is a truly breathtaking example of integration in science, perhaps the greatest in the whole history of science. In one stroke, two fields which had been studied completely separately, electromagnetism and optics, which were two separate fields, in one stroke, the two were integrated into the same field, with optics, the study of light, turning out to be merely a derivative or aspect of electromagnetism. And what was the agent or means of integration here? Not experiment. As usual, it was mathematics, the manipulation of equations. Granted, those equations were based initially on observation and experiment, but it was only their manipulation, only the derivation that they made possible that led to the identification of light with EM waves. Now I must confess, I guess that's the word, that it was later discovered that light had certain properties besides those predicted by Maxwell, so that there were some defects in his viewpoint and some alterations in his view of light have proved to be necessary. But this does not alter the validity of the essential conclusions which he reached, and which are still accepted today. I might add that today's light theorists do not have a coherent theory of light to replace JCM's. To my limited knowledge, the most they can say is that light has both the characteristics of a wave and of a particle, even though these are defined as incompatible phenomena. So, offering no explanation, today's theorists in the typical 20th century manifestation resolve the dilemma by calling light a wavicle. That has to speak for itself. In any event, as to JCM's achievement, I quote again from Dave, all the data earlier accumulated about light waves are proved to be really data about EM waves, i.e. about the disposition of electric and magnetic fields. So all the data about light, therefore, are predicted by JCM's equations, unquote. Thus the integration of electromagnetism and optics, and thus the mind of a true genius. I think it should now be clear to you the crucial role of math in this man's immortal achievements, its role in his ability to state the basic laws of the field, its role in integrating all the previous EM data, and its role in making astonishing universal inductions purely by mathematical deduction from his equations. Inductions subsequently proved to be true experimentally. So for JCM as for Newton, mathematics is the key to scientific method and to induction. So I've shown you now from every aspect that I know that math is indispensable. There is simply no physics without math, without numbers, without measurement. And it doesn't matter whether we talk of an experiment that leads to a narrow law or of inductive leaps to the most universal law. At every point, math is inescapable. Without it, there is simply no physical science. Now, so far, the question which we already flirted with in Lecture 1 insistently recurs. Why? I haven't given you any reason why math is indispensable. Why nothing else could ever, even in theory, work in its place. I've merely stated that math is of the essence and shown you physicists repeatedly counting on it. Now, but why? What underlies this? What is the deepest source of the necessity of math is a topic I'm going to happily explore and, in my opinion, answer decisively in Lecture 5. So don't miss that one. All right, draw a line. We get now to the large topic for today, after which will be another brief topic. And this topic, if you want a title, you can call The Validation of Inductive Fundamentals. The Validation of Inductive Fundamentals. In mechanics and electromagnetism, two fields we've been taking as paradigms of induction, we reached, in the end, a set of very broad gens which identify the fundamentals in the field and explain the previously accumulated observational and experimental data. Now let us ask the final inductive question in regard to the methodology of induction. How do we validate the ultimate fundamentals themselves? By what epistemological standard can we claim to give a conclusive proof of the last, widest fundamentals in the field? Now, they're obviously not self-evident. On the contrary, they're the farthest removed from direct perception. They are as high up the hierarchy as we can go. And they are so broad by their nature, so all-encompassing, that no experiment or grouping, no chain of mathematical deductions alone can establish them conclusively. For example, Newton reaches the ISL of gravity by mathematical derivation, as we saw, from the law of circular acceleration and Kepler's third law, which are laws governing the motions of the planets in our solar system. And he then supplements this proof by calculations showing that the apple and the moon also obey the inverse square law. But then he leaps. He generalizes to the entire universe. He says all matter. Now we're asking the question, how can he do it? How can he go? Planetary orbit, moon, apple, all of which occur in one little place within a vast universe. How could he leap from that to a conclusion about that total universe? And a similar leap was followed by JCM and electromagnetism. All explanation and understanding within a given field of physics ultimately depends on these broad fundamentals. But how do we validate them? Now, clearly these principles are primaries, at least within our knowledge. So we can't count on deriving them or deducing them from anything deeper. There's no infinite explanation, no continual asking of why. For example, to this day at least, we can't ask or answer why is the law of gravity true, or why does motion obey Newton's laws, or why does an electric current go at right angles, why does a magnetic current go at right angles around a current-carrying wire. We can ask some really basic whys, like why light has a certain speed of propagation, and answer in terms of the electromagnetic waves derived from JCM's equations. But about the ones I mentioned before, we cannot ask why. The fundamentals are simply the given. They are in each field the equivalent of existence exists. They are the form existence takes as a primary in each area. And you wouldn't help yourself in this connection, even if you found some way of explaining these fundamentals in terms of still other, even more basic principles. Because these other principles themselves at some point still have to be primary. You can't have a situation where all explanations themselves are explained ad infinitum. So the question is, how can we know and validate objectively principles as wide and fundamental as these? How can we possibly go validly from observations made within our little planet, including the comparatively few heavenly bodies, comparatively few, accessible to our instruments? How can we go from this seemingly meager evidence to universal laws, encompassing an unlimited field of material objects across an utterly immense time and space? I'm trying to make you feel that this is a problem. Experiment will not take us that far. Mathematics will not take us that far. Not the kind of math that's just derivation from experimental results. So what then does? Now I want to get rid of a false answer. The answer most prevalent among philosophers and scientists today, the so-called hypothetical deductive method. It isn't even worth writing it down. That's the view which says, well, if a theory does predict in all the observed data, it must be true. So we put forth a hypothesis, and we deduce from it its consequences. And then we look out and say, aha, those consequences are true, therefore the theory must be true. That is, of course, a logical fallacy. If you're a man, therefore you're mortal. This pig is mortal, therefore it's a man. That is the same form of reasoning, and obviously invalid. What you have to be able to say to validate fundamentals is not, this theory explains the data, but one crucial word has to be added. Only this theory explains the data. We have to be able to say, not only does our theory do the job, it is the only one that can. No other theory is even a possibility, which is a much greater demand than predict some consequences and say, oh yeah, they're true. So now I'm going to make you feel the question even worse. How can we, with our limited knowledge, and that's our nature, ever be in a position to know no other theory will ever be possible? The standard response, if you say this to anybody in philosophy today, is maybe what you think of as impossible in terms of a theory is simply a reflection of the poverty of our imagination or the limitations of our knowledge. So again, the question, what is the objective proof of the widest fundamental? Now I'm going to give you my answer in a single sentence without preparing you, and then the whole next part of the lecture will be illustration and validation of this. This is my answer, not Ayn Rand, so I get the credit or the blame. She gets the credit for getting me to the point where I can talk, but then I don't want to saddle her with this particular theory, although I regard it as true. A broad theory is true when it represents an integration of diverse fundamentals within an intensively studied area. A broad theory is true when it represents an integration of diverse fundamentals within an intensively studied area. Now let's take that instead. Notice that I say an integration of fundamentals. So it is not enough by this definition that you integrate a random series of data, however extensive. I say that to reach and validate the broadest universal, you must first organize diverse fields of study, at least two different fields of study. You must organize each of them in terms of fundamentals, so that within your knowledge, you've already bound together into a unity all of the data in each field. And if you can then integrate these fundamentals into a still broader set of principles, which explains the fundamentals in each of the various subsumed areas, that is what I mean by an integration of fundamentals. And that is what I regard as the validation of the deepest fundamentals of science. Now notice that implicit in this is the fact that my criterion applies only to intensively studied fields. You cannot know fundamentals in any area until you already have a wealth of data accumulated in that area, because a fundamental is by definition that which underlies a whole development, a whole set of data. And notice also that when my criterion is fulfilled, you are entitled to say only. You are entitled to say only this theory explains the data. Now why? Because all the data have already been consolidated into units under fundamentals. And this very unification in itself will point in the end to a single ultimate unifying theory. In other words, the earlier ascent to lesser fundamentals will eliminate other approaches to the question and point the way in due course to a single possible culmination. At that point, any other candidate would not be just, subjectively inconceivable. It would be objectively arbitrary, which must therefore be dismissed from consideration. Now I'm going to give you an analogy. It's just an analogy, but it's a helpful one. An analogy to an author writing not a modern novel, but a well-structured novel. At the beginning, he's faced with an enormous wealth of possibilities. The novel could go in 100 different directions, even with the same theme and character. But the farther he gets in the writing, the more he defines and lays down the essence of the characters in the story, the fewer his choices become. Until near the end, writers typically report that their writing races to the conclusion, because the choices by that point are severely limited and even dictated by the wealth of material and the structure already established. And that's what happens essentially in science. When several fundamentals in different fields are consistent with each other and each integrate all known relevant data in its field, so that there is no basis in any given field for any other theory. And there is only one still more fundamental theory that unites all of these fundamentals. Well, that's the one I call a super integration. That's my homey term for it. That's my term for the integration of fundamentals. The one which is the super integration in that context has been proven to be the true one. This is my theory of validation, not just by integration, but by super integration. And no such super integration will ever be overthrown, because all future knowledge in these cases has to be built on. I think this is pretty obvious if you think about it, this criteria. The widest universals, which perform the widest integration, must be established in the only possible logical way, by showing that they do indeed perform the widest integration, and that nothing else does so, as proven by the fact that what these universals integrate are the fundamentals of all the subsumed areas. Now, Newton's laws of motion and gravity, for example, I've already suggested. explain and integrate all the basic discoveries, both in astronomy and in physics. And here was truly an integration of fundamentals in two intensively studied fields. Newton's ultimate conclusions were not reached and validated from direct observation alone. Each observation and lesser law explained by Newton had been separately validated, and each had been united into a fundamental of sorts in its own realm. But it was only Newton who put it all together, deriving everything in mechanics, both terrestrial and celestial, from, in effect, two basic laws. Now, typically, the passage from possible to probable to certain is apparent on the highest level of generalization, the kind we're talking about now. Such passage does occur on earlier levels also sometimes, but often it does not. In the typical experiment, for example, the inference is at once apparent. The experimenter, such as Galileo or Michael Faraday, goes from a hypothesis to certainty in one leap. But for the very broad generalizations, typically, you accumulate and organize the evidence in the various subsumed fields gradually, painstakingly ascending the ladder of validation, reaching a fundamental here and a fundamental there and a fundamental there until in the end you hit the epistemological jackpot. Now today I want to work through one example of validating a broad universe, and this is the theory of atomism, that all matter is composed of tiny particles as against it being a continuum. And I'm just discussing this only to illustrate my theory of superintegration. And I can only do this in pattern, touching on several highlights of the total story. But I want to show, at least give you an indication, how the theory of atomism progressed from possibility through probability, and at what point and how it became a certainty. Again, you will find that it is important to grasp some diversity of data from different fields. And even if one point I present is too brief to be clear to you, try and grasp some steps in one field and then another field, so you get the idea that the evidence is pouring in from a bunch of different areas, even if you don't get any one. So it's like with Newton. As long as you get a few steps, you can project the other steps are like that. And the same thing here. If you get a few pieces of data, like from heat or from chemistry, you can project the others and fill in and get the idea. Now, of course, if we were to develop the atomic theory right to the subatomic level, it would culminate, as you would expect by now, in a series of mathematical equations, just as classical mechanics and electromagnetism did. But today I am not going to continue on to the mathematical finale because we're interested in induction, and you already know the importance of the mathematical side of induction. I want to concentrate instead on the issue of the integration of fundamentals and the gradual passage to certainty. So I'm stopping at the point where scientists have proved that matter does consist of atoms. By the way, I'm going to use atoms or molecules more or less interchangeably because both of them represent matter being particulate, made of particles, as against being a continuum, or what was called being a fluid in those days. A fluid is a material that acts as a whole and is not made of separate particles. And I'm not doing too great a violence in this usage because a molecule is just a combination of atoms anyway. So if molecules exist, atoms must exist. So the atomic theory is a vast universal. It applies to every material object throughout the universe. How can we possibly prove its applicability to every material object, confined as we are, and I repeat, to one insignificant planet lost in one garden variety galaxy? Now, some of you who know the history of philosophy say, oh, well, there's nothing to this because Democritus in ancient Greece proved the atomic theory by pure philosophic deduction. That is false. Democritus offered purely rationalistic explanations, taking for granted as self-evident, unproven, or even false principles, such as his principle that motion is impossible in a plane. The ancient atomists did have a great idea. They were the ones who gave the moderns the idea of atomism, but they themselves had no more proof of it than Plato did of his theory of form. And that's why most Greeks, including Aristotle, legitimately considered atomism as just one more arbitrary or mistaken philosophic theory, and not at all as objective science. So let's plunge into the modern era. And let's take an early example of some evidence for atomism. Here's a fact. Count Rumford put some cannon in large vats of water, took very dull drills, and started to bore holes in them while they were placed in the water. And the result, he didn't do anything in the water, he just bored holes in the cannon. The result was that the temperature of the water rose and the water turned into steam. What could be the explanation of this? Well, it seems to be that heat is related to motion. That heat is motion, because motion is all of the drilling introduced. That's all they put into it, the motion of the drill. But what kind of motion would it be? The water as a total remains stationary within the vat. So it must be some kind of internal parts of the water that are receiving motion, that are getting hot. And what would these internal parts be? You can't see them. Atoms. Now, the fluid theory, on the other hand, what would they say about an experiment like this? If heat is a fluid, one continuum, how could drilling create an endless supply of this fluid, which it would have to do to explain the rise in temperature? So you say, okay, that's it, we proved the atomic theory. No, you haven't. All we can say at this point is, we're not yet clear. We can't imagine how the fluid theory would work, but that's not good enough even to qualify the atomic theory as possible. If you remember OPA, possible requires that you know what proof would consist of, and also that a given step moves you in its direction. But we don't even know that here. Only then could we say we have some evidence. We haven't established even that much. And on top of that, before you get too complacent, we have doubts even here. If heat is a movement of atoms, how does that explain the role of heat in changing the form of a substance? In other words, changing water into steam, which is a different phenomenon than simply raising its temperature. Nobody could say at this point. And again, as against the fluid theory, how could motion be transferred in such a way as to be conserved? Now, it was known earlier that heat is never lost, merely transferred. A simple example, if you pour an equal amount of cold water into warm water, they reach an equilibrium point halfway between the two original temperatures. Heat is conserved. Now, if heat is a fluid, it's easy to see how it could be conserved. Some of the fluid would just pass from the warm water to the cold water. So Thomson seems to have raised a possibility, but no more. And even so, he's shaken by doubts at this point. So the most we could say at this point, out of generosity epistemologic, is to say, maybe this is a possibility. In other words, we can't say maybe, but only maybe. We have a very narrow base for atomism at this point. Some data about heat. Seemingly conflicting evidence also. With evidence so slender and ambiguous, it is too early to declare a possibility. Well, now let's add in some early evidence from chemistry, which at this point was an entirely separate field from the study of heat. Specifically from chemistry, the discovery of how elements combine into compounds. There's several laws governing this, but I'm going to jump in and give you one of them, the law of definite proportion. The law of definite proportion. It was discovered by experiment that elements combine only in fixed proportions of their weights. Proportions expressible in simple integers, 1, 2, 3, etc. For example, you could take 3 grams of carbon and 8 grams of oxygen and put them together, and you would get 11 grams of a certain compound. Both of the constituents would be completely used up. But, if you took 3 grams of carbon and 9 grams of oxygen instead of 8, what do you think you get? You get the same 11 grams of that same compound plus 1 gram of oxygen left over. You just can't make the 3 and the 9 form a compound. Laws of definite proportion. Plus, there are no cases where 3 grams of carbon combine with fractional amounts of oxygen. There's no such thing as a compound reached by 3 grams of carbon and 6.5 of oxygen. Now, what could explain this? I quote from Dave. He's an endless source of quotes because he says it succinctly and essentially, which no other physicist in the history of man does. At least to my knowledge. Quote, if matter were a continuum, why would elements combine, this is Dave, only in exact integer ratios of their weights? Why not combine in fractions, such as 3 grams of carbon combining with 1/2 a gram or 7.2 grams of oxygen? The answer, elements are made of atoms and compounds are combinations of atoms, and there is no half atom or fractional atom. Now where are we? We have a lead from the study of heat and some evidence from chemical combination. So we have 2 diverse fields of study starting to point in the same direction. We're integrating data from 2 different fields. So I would say logically at this point we can say, hey, maybe. In other words, I think we have established now a real possibility. Of course, it's really premature to talk about probability here. Why? Because there are areas of science intensively studied, not even heard from, such as electromagnetism, such as mechanics. And we know that we're only at the start of the scientific study in these areas. That we haven't studied intensively even chemistry and heat, and that no fundamentals have yet been established in these areas. So it's way too early. All we have is enough early data to say it's a possibility. Okay, now I'm not going to eke it out 1 inch at a time. I'm going to take a jump to the point where there are signs leading to probability. Now here you have to take something from me without explanation because it is beyond my power to condense the context here. You just have to take it from me that at one point the atomists ran into trouble, and the only way out was to make what was to them a startling assumption. Namely, that if you took equal volumes of different gases, you know what a volume, like in a container, 1 liter or 1 cubic foot, they had to make the assumption that equal volumes of a gas must contain equal numbers of molecules. Even when the gases were very different, even when their molecules are very different, even when the molecules have very different weights, they had to accept the idea it's still true that equal volumes contain equal numbers of molecules. And they wondered, why should this be true? It would, as I say, get them out of a difficulty that they got into, but we can ignore that and just plunge into it. Well, at this point, a scientist you may have heard of named Avogadro took the bull by the horns and put forth this seemingly perplexing theory as a hypothesis. And of course, it's part of the atomic theory because it's based on the idea of gases being made of molecules. Avogadro found that not only did his theory make comprehensible the law of definite proportions, but it also enabled him to determine relative atomic weights. How much one atom, say the oxygen atom, weighs in relation to the lightest element, hydrogen. And it turns out that the oxygen atom is 16 times as heavy as the hydrogen. If we neglect here the distinction between weight and mass, and we're allowed to in this context, it means we can now determine the relative masses of two different atoms. And this was potentially a very big step because it opened the door to measurement on the atomic level. Measurement of relative atomic masses. All of it, not absolute numbers, but relative to hydrogen taken as the unit, the light. Now the reasoning of the atomists here is this. Since 1 liter of any gas, 1 liter being just, a volume, since 1 liter of any gas has the same number of molecules, that's Avogadro, then the ratio of the mass of 1 liter to 1 liter of hydrogen must be the same as the ratio of the mass of one of the molecules to that of a hydrogen molecule. And this is going to be crucial in the further development of chemistry. And after it's discovered, also thanks to Avogadro, that some molecules are diatomic. You know what that means? Their molecule is made of 2 atoms joined together. So their symbol would be H2 or O2. That represents the hydrogen molecule. It doesn't exist as just a single free-floating atom. It's diatomic. Well, after it was discovered, thanks to Avogadro, that some molecules are diatomic, we can then translate a ratio of molecular weights into a ratio of atomic weight. And note that, of course, as I said, Avogadro's hypothesis assumes that there are atoms. The whole thing is the number of molecules in a given volume of a gas. So can we jump to probability now? No, because there's a new question. How can we reconcile our atomism with data coming in from experiments on electricity, and specifically electrolysis? Now, I don't think we covered electrolysis in this course, did we? In essence, you run a current through a substance, breaking it up into its constituents, one of which, or some of which, then migrate to a positive plate, and another to a negative plate. Well, they did this with substances containing hydrogen, and when the hydrogen atoms were released, when they were freed by the current, they showed up as electropositive. In other words, they went to the negative plate. You know that negatives and positives attract each other in electricity, just as north and south poles attract each other in magnetism. So hydrogen atoms showed up as electropositive. Yet hydrogen is diatomic. We knew that now too. And if it's diatomic, both atoms must have the same electrical nature. They must both be positive. So why do they cling together instead of repelling each other as two positives are supposed to do? That is a baffling question at this stage. They had no distinction yet between an atom and a charged atom, or what we now call, thanks to Michael Faraday, what's the name for a charged atom? An ion, I-O-N. But they didn't have that distinction. So to them it was a mystery that a diatomic gas should behave so that the atoms should cling together with the same electrical form, or positive or negative. So you couldn't claim probability yet because you're completely in the midst of a total confusion which stops you cold. And this is typical of the path that a complex basic fundamental has to go through. Good news, problem, doubt, great news, still a question, an answer. Oh no, but what about this? All of it pouring in as scientists study more and more. All right, now some good news from the heat front again. A new fact was discovered. It's like a war between the fluid people and the atomic people. And since we know who won, we call good news what comes in to support atomism. Oh, thank you. A new fact was discovered. The law of constant heat capacity. The law of constant heat capacity. Now, the heat capacity of a substance is defined as the number of calories required to raise 1 gram of the substance by 1 degree centigrade. The heat capacity is the number of calories required to raise 1 gram of the substance by 1 degree centigrade. And now, guess what they found? If you take the heat capacity of a substance and multiply it by its atomic mass, we reach a constant. The same for most substances, not all, but most. How would you explain this? Heat capacity measures the heat required to raise the temperature of a gram, the unit of mass, by 1 degree. An atomic weight measures the mass of one atom in relation to the mass of the hydrogen atom. So the product of these two must lead to the heat capacity of what? Of one atom of the material. In other words, try to restate it this way. 1 gram of a material contains fewer atoms as the atomic weight of the atoms becomes greater. If you get 1 gram, it takes fewer atoms if the atoms are heavier. So if you multiply heat capacity by atomic weight, you cancel out the differing atomic weights and end up with the heat capacity of the same number of atoms of each material. And since this product is almost always the same number, it has to follow that every atom must have the same heat capacity. Because if two bodies with the same number of atoms have the same heat capacity, every atom of each must be absorbing the same amount of heat. Now, this is another striking piece of evidence for the atomic theory. I quote again from Dave. The heat capacity of substances can be explained simply by observing that each molecule absorbs about the same amount of heat, unquote. Now, by contrast, how would a continuum or fluid theory of matter explain this fact? Well, presumably on such a theory, there should be no such thing as atomic weight because there are no atoms, nor therefore any relation between that and heat capacity. How then would it explain the fluid theory? How would it explain the varying heat capacities of substances? Now, no one actually developed a rival continuum theory. But the idea was not discarded because some phenomena, important phenomena like light, being regarded as wave-like, seem to imply some kind of continuum theory. Still, there is now a real, if small, bit of probability to the atomic theory. By this point, it's no longer just a maybe, because both heat and chemistry are starting a bit more to point in a similar direction. Now a new fact for atomism from chemistry. Isomers. I-S-O-M-E-R-S. They discovered isomers, that is, compounds made of the same element, in the same proportions by weight, but nevertheless different compounds with different properties. For example, you take ethyl alcohol, which is a constituent of liquor, and methyl ether, which is an anesthetic. On the face of it, really, really different substances. But they actually prove out to be isomers. In other words, they have exactly the same elements in exactly the same proportions by weight. Now, how would you explain this? Well, the atomist explanation is there must be a different organization, a different structure of the same atoms within the molecule. Same elements, same amounts, but put together differently. And that implies, of course, that two substances have different internal structures. In other words, atoms combining differently. What else could explain the data? So the atomic theory is becoming another bit more probable. But remember here that a theory as universal as atomism needs evidence drawn from all key areas where we have knowledge of matter. It must cover not just data from chemistry or heat, as so far, but also from all key areas of physics. For example, electric charge. It must be integrated, in short, with the whole range of intensively studied phenomena. So now a new fact. The first integration of atomic theory with electromagnetism takes place. Michael Faraday's electrolysis experiments, which I briefly referred, show that matter carries charges in integral units. Now, I have to leave out the details of his experiment, but they seem to show that electricity comes in discrete units. And it then seems logical to conclude that those discrete units are carried by discrete units of matter. So, for example, when electricity breaks up a compound containing silver, for instance, silver nitrate, and the freed silver is allowed to accumulate on a charged plate, the new charge on the plate from the silver ions bears a 1-to-1 ratio to the weight of the silver atom. For example, 50 silver ions lead to 50 units of charge. So silver seems to carry a charge of 1, whereas lead, it proved out, carries a charge of 2, and so on. But it's always whole numbers. There was never 50 silver atoms freed and 49.6 units of charge received. How could a continuum theory of matter explain this integral nature of charge? Why no charge of 1.3 units or 6.1 units being transferred? Again, we seem to be led to the inference that charge is carried by discrete bits of matter. In other words, by charged atoms, or what Faraday called ions. Now, Faraday's electrolysis experiments are the first evidence for charged atoms, but they in no way yet prove atomism conclusively. The fact that electricity comes in discrete units does not necessarily imply that those units are correlated with particles having a certain weight. For all we know at this stage, silver, for example, might have 1 charge, while other elements have 2 or 3, simply in virtue of the differing nature of these elements, and not because of any atomic constitution. Nevertheless, Faraday's was the first good evidence that atoms, if we assume they exist, can become charged, and only in integral multiples of some unit charge. So our context is that the evidence is piling up in the study of heat, from the laws governing the combination of elements, and isomers, from the studies of charge. You see, our theory is becoming more and more probable. Now a big contribution from physics, and actually from the mechanics of Newton we're going to bring in here now. Now I'm referring to J.J. Waterston's ideal gas law, also called the basic atomic gas law. In caps, first letter, ideal gas law. And of course, like all laws, it's a generalization. This is going to be very important Because if you establish something as universally true of a gas, then you have established it as true of all matter, since every element of matter at a high enough temperature turns into a gas. That was an earlier generalization. Now the gas law is reached, starting with Newton's laws, and then just manipulate, mathematical deduction. It assumes that any gas can be construed on the billiard ball model, with point masses being substituted for billiard balls. The various masses then striking each other and rebounding, etc., according to Newton's laws of motion. And this, of course, is a form of atomism. So the gas law assumes atomism. Now, by a complex mathematical process, which we're very simply going to skip, the following law is reached. Look to your handout, and I state there the gas law. PV is proportional to NMV squared. Something I'm sure you always know. P is the pressure on one wall of a gas's container. V is the volume of the gas. And the product of those two is proportional to N is the number of atoms in the container, M is the mass of each atom, and V is the atom's velocity. So that's the ideal gas law. Now we'll use it in a minute. Now I have to look back for a minute and tell you about an earlier crucial concept that had been formed by physics, and it was going to come in here. And that is the concept of energy. Now you must know just from observing technology today and the atom bomb how very crucial this concept is to physics. Well, energy was defined as the capacity to do work. And work means exerting a force through a distance. For example, if you move a pound through a distance of a foot, you have done a foot-pound of work. And the capacity of an object to do this much work is, let's say, 1 unit of energy. Now it was found empirically, simply by observation and experiment, that energy could be transferred from one type of reaction to another. Heat energy could become chemical energy, which could become electrical energy, etc. And in each case, they found, as a matter of observed fact, no energy was lost. The same amount was merely transferred from one form to another. So they formulated the law of conservation of energy. Energy can't be created or destroyed, merely change its forms, merely transfer from one form to another. Now this was a brilliant new integrating concept, energy, and the resulting law, which was obviously dependent on that concept. If you know the subsequent development of physics, this is another striking illustration of a concept being a green light to induction. I hope someone will ask me the question, in what way was the concept of energy and its associated law of conservation of energy a green light in physics? Because Dave gave me 12 ways in which it produced startling new discoveries, and I've got 3 of them ready to tell you, but if you don't ask, you won't know. Now, 2 types of energy were soon distinguished: kinetic energy and potential energy, KE and PE. Kinetic energy is energy possessed through motion. A moving object obviously has the capacity, when it strikes another object, to exert a force on it and move it through a distance. That's kinetic energy. Potential energy is energy not through motion, but through the position in a field. The simplest example is a stretched spring. Certainly has the capacity to do work. It still has energy, and will actually do the work when you let it go. And the formula for these, before Waterston, had been worked out. And kinetic energy, they found, could always be captured by the following formula: 1/2 mv squared, where m is the mass of the moving object and v is its velocity. 1/2 mv squared. All right, now, let's take the gas law, and we're going to assume a fixed number of atoms in the gas that we're looking at. So we can drop the constant and write that, we can just drop the n here, because we're assuming it's a constant, and proportionality remains the same whether the constant is there or not. We can write PV as proportional, if you look at that law. PV is proportional to mv squared. But mv squared is, leaving again aside the constant 1/2, is what? The formula for kinetic energy. So from the gas law, combined with what they knew previously about energy, we can say that the product of the pressure and volume of a gas is proportional to the kinetic energy of its constituents. But now I want to tell you another law that had been discovered earlier by a scientist named Charles. And his law, of course, was Charles's law. And he had a purely empirical law, which also dealt with the product of pressure and volume. His law was that, I didn't write it down because it's too simple. PV is proportional to T, that's the temperature. For example, if the temperature is constant, then if you let the pressure go up, the volume has to go down. And the product of those two varies as the temperature does. So, what must follow? If PV, the product of those two, is proportional to kinetic energy, and PV is proportional to the temperature, doesn't it follow that the temperature must be related to the kinetic energy? Because both are proportional to the same quantity. In other words, if you combine the gas law with Charles's law, then you get PV is KE and T must be related. And what could temperature be then besides the measure of the kinetic energy? Not, of course, of the gas as a whole, because the gas as a whole isn't moving, but of the internal constituents, the internal atoms or molecules making up the gas. Here we have the atomic theory used to explain the nature of heat, its exact relation to motion, and exactly what form of motion, 1/2 mv squared, is conserved in heat transfer. Now this is a big step forward. Plus, the atomic gas law, which is a wonder, also explains Avogadro's hypothesis. Remember that the same volume of any gas must contain the same number of molecules, regardless of the type of gas. Because, given the gas law, at any given temperature and pressure, the volume is proportional simply to the number of molecules, regardless of what kind of molecules the gas is made of. The gas law takes into account only the number of molecules, not the nature of the molecule. So the same unit volume of the gas, assuming the same temperature and pressure, the same unit volume of every gas must contain the same number of molecules, which is precisely Avogadro's hypothesis. Now we are getting somewhere and making the atomic theory really probable. Because the atomic theory alone now explains both Charles's law, that PV is proportional to T, and Avogadro's hypothesis, while also integrating with the early knowledge that heat is conserved, and also with Thomson's discovery that heat is really motion. So is this the end then of the validation? Have we got enough? No. Because even all of this would be fine if the billiard ball model of the gas, which we've been assuming is really true. But a critic could legitimately say at this point, if atoms do not behave like your billiard ball, then all the explanations offered by your model are bogus. And the atomic theory has not yet been proved at this point, despite the fact that the gas law explains so much. Because there are still rational doubts about the billiard ball model of gases on which the gas law rests. So what we need is an independent confirmation of the ideal gas law. If something from the outside could show this, and then it shows all these other things, then we're getting a real integration. Furthermore, to make the situation bleaker for a moment, there's now a new doubt from another quarter. We can describe the new doubt as the slow rate of dispersion of gases. For example, if I take a smelly gas and put it across a large room, on the one hand, the atom is held, the molecules of the gas move very, very rapidly. And on the other hand, it takes the gas seemingly forever to get over to our part of the room. Now, how can we put these two together? It seems on the face of it, certainly a paradox. Guess who wrestled with this issue and ultimately solved it? James Clerk Maxwell. He is a creative giant here too, not just in electromagnetism. And he discovered a crucial fact about pendulums. He discovered a fact about the rate at which pendulums damp. You remember that they're said to damp when they gradually get lower in their swings due to air resistance until they finally come to a stop. Now let me say what the intuitive view on this question would be. The view held by most of us and by most scientists at the time on this question. It would be that the rate of damping, if you put a pendulum in air or in any gas, the rate of damping, we would think, is in part at least a function of the density of the air, of the mass of it per unit volume. For example, if I asked you, if you compress air 10 times, so you get 10 times as many air molecules in the same small volume, wouldn't this highly compressed air greatly speed up the damping of the pendulum? It just seems common sense that the density of the air would contribute to the air resistance, slowing up the pendulum more rapidly and ultimately stopping it. Doesn't that seem common sense? I mean, obvious. Well, now, get this one. Assuming the billiard ball, the atomic theory of gases, and then simply deducing from Newton's laws, JCM predicted, here again, purely by mathematical derivation, he predicted the astonishing result that the density of the air, within certain limits, is irrelevant to the damping of the pendulum. Or in other words, that density, whether the air is normal, or this could apply to any gas, but we'll use air. The density, whether normal or 10 times compressed, is irrelevant to air resistance. He deduced that from the atomic model combined with Newton's laws, that the density is irrelevant to air resistance. And he made the full statement of that in 1867. Now, he himself, JCM, believed that he must have erred in this conclusion, because it seemed like a fantastic, bizarre prediction. And yet, in fact, his prediction was soon experimentally verified. And this was a really big turning point for the atomic theory, because it seems impossible to explain this result if air is a continuous fluid. It would be like saying that the density of mercury as against water has nothing to do with the differing resistance each offers to a man trying to swim through it. If a gas were a continuum, then by definition what a continuum does is operate as a single whole, all of it thereby affecting and retarding the pendulum. Hence, the more dense the gas, the greater the damping would have to be. But now contrast the situation with the atomic theory, because there a gas is viewed as particulate, as made of discrete particles, and therefore those particles are capable of separate individual action. So it's at least possible for only part of the gas, some of the particles, to affect the damping, while the others don't. And therefore it's possible that packing in more particles won't affect the damping, because most particles can somehow be shielded from acting on the pendulum. In essence, they found that they won't hit the pendulum because they're busy hitting each other. And therefore the same number end up hitting the pendulum. There's no effect on the air resistance. In other words, the ability of a gas to act in part rather than as a whole is essential to explaining the irrelevance of density to the resistance air of. So what started out as a real problem for the atomic theory, this bizarre prediction, ended as a major confirmation of it. Now, for the first time, chemistry and physics, instead of being pursued as separate, self-contained subjects, as they had been until that time, began to be integrated into one field, and the integrator was the atomic theory. Now, I'm going to take a 5-minute break here and then finish up the atomic theory and our last topic. Now, I was saying that chemistry and physics, which had been pursued as separate, self-contained subjects, began to be integrated into one field, and the integrator was the atomic theory. Here is a perfect example of the integration of fundamentals by an even more basic fundamental. Chemistry had organized its data. Physics had organized its data, and now the atomic theory organized the organizations. And the key link here was Avogadro's hypothesis. In physics, as we saw, the ideal gas law explained why Avogadro's hypothesis had to be true, and therefore explained all of the results of that hypothesis in physics. While in chemistry, Avogadro's law, as we have seen, was central to the discovery of atomic weights, which were the only means chemists had to reach the formulas of various substances, such as H2O, NaCl, etc. And these formulas in turn made possible to chemists the concept of valence, which I'll tell you about in a minute, and thereby with other data made possible the famous periodic table of the elements, which was created, all capital P and T, periodic table of the elements, created in 1869 by the Russian chemistry teacher Mendeleev. And that periodic table integrated in one system a huge amount of previously disparate chemical data. So what is the overall evidential picture now? In essence, there were ever more chemical data coming in, all made possible by Avogadro's law, which thereby became further evidence for the ideal gas law, which was the law that proved and explained Avogadro's law. And remember, it used as its base Newtonian mechanics. So you see, it's all coming together under the principle of the atomic theory. Now, I want to look for a minute now at this fabulous achievement, Mendeleev's periodic table. It relied on the concepts of atomic weight and of valence, both of which rested on the atomic theory. Now, valence, that's V-A-L-E-N-C-E, is another crucial concept, making possible a whole host of generalizations. But it really means the number that states a given atom's power to unite with other atoms. For example, a valence of 1 means that that element can unite with only one hydrogen atom, whereas a valence of 4 means that a single atom can unite with up to 4 hydrogen atoms. The periodic table relied on the established knowledge of the valence of the different elements. And also, there had been the discovery of what was called families of elements. In other words, clusters or sets of elements which reacted in similar ways with other elements and compounds. Now, Mendeleev integrated all this chemical data into one intelligible whole, as against a chaos of 60-plus different elements known at the time, with their characteristic reactions unrelated, at least in any systematic way. He created a table that organized the known elements, both by families, the members of which always have the same valence, and by atomic weights. Now, there had been previous attempts to discover such patterns. But Mendeleev's was the historic success because he was the first to include and organize all of the known elements, plus he had another great idea. He was willing to leave vacant spots, blank spaces in his table. In other words, when he was filling out the table, if the next atomic weight that was known at the time did not represent the family or have the valence that the table required, he simply left the spot vacant, on the premise that the element properly belonging there was still unknown. So to fill his empty slot, he predicted 6 new elements, all as yet unknown. And by the gaps in the atomic weights which he knew, he was able to predict the approximate atomic weights of these missing elements and many other characteristics, including the families and therefore many of the type of reactions that they belong to. And his predictions were triumphantly proven right in due course. So we're ready now to sum it all up. Dave believes, and certainly convinced me, that by the 1870s at the latest, we have the final definitive proof of atomism. And this is true even though there are many later evidences, including the phenomenon of Brownian motion you may have heard of, which seemingly reduces atoms to the perceptual level where you can actually see them. And of course, the Brownian motion, is commonly taken by modern scientists, the ones who believe you can prove anything, as the real proof of atomism. But this is an error of stunted minds on the perceptual level and places the date of proof much too late. By about 1870, Dave thinks, the atomic theory had been conclusively proven through the joint evidence from chemistry and physics. Both were coming in their fundamentals to the same conclusions, and therefore the two subjects were growing together and becoming interconnected as we now know them to be. Physics was providing the ideal gas law, on the basis of which Avogadro's law, including its many explanations, were derived, and also JCM's many verified predictions came from the same ideal gas law. Meanwhile, chemistry was verifying the gas law independently by showing the necessity of Avogadro's law to the understanding of chemical reactions, culminating in Mendeleev's periodic table. By 1870, physics and chemistry together had provided an unanswerable proof of the atomic theory. I've just given you some highlights. But here is an excellent example of a decisive proof being achieved, not by a single experiment, or even within a single field, but specifically by means of an overarching connection, a super integration, as earlier defined. Now, you have to note the necessary contributions of all the various fields and pieces of evidence. The atomic theory of gases explained observations in regard to damping, heat conductivity, particle diffusion, and also explained the nature of heat. That's great so far. But it did so by hypothesizing the billiard ball model of gases, which was not obvious. So even if the law does integrate the gas law, a significant amount of data, including Avogadro's hypothesis and Charles's law, this is still too slender a range of evidence to draw conclusions about all matter. Out of context, one couldn't say, if that's all you had, this is the only explanation. But given a context strongly favoring atomism, growing out of chemical and electrical studies, the gas theory could then be the culminating piece of evidence necessary to conclude to atomism. Now this process that we've traced out in pattern, in my judgment, is always the method of validating the broadest universals. Its application, as you see, the precise point at which you pass from possible to probable to certain, is debatable within certain limits. And there's no way to quantify this validation. You can never say anything like, once you get 28 pieces of evidence from 4 fields, you've validated your jet. And I'll give you the reason why you can never hope to do this, to quantify it in Lecture 5. But the issue of quantifying the evidence is irrelevant, because the legitimate debate is always within very narrow limits at this point in the hierarchy. It is in almost every case easily resolvable, being merely an academic inquiry into whether, for example, the atomic theory was officially established as conclusive in 1867 or 1871. You can disagree on that. The crucial point is that the principle of validation through an overarching superintegration of fundamentals is an absolute, and is the answer, in my opinion, to the hardest part of the problem of induction. I think you see now how Newton or Maxwell or the atomists could go from a seemingly highly limited amount of data, taken from a narrow corner of a vast universe, to conclusions applying to the whole of that vast universe. In the face of it, an impossible assignment, bemoaned by philosophers for ages as impossible, and yet one achieved time and again by the proper exercise of the human mind. In other words, by following the right method of induction. And let me add here that all the fundamentals we have discussed have been upheld to this very day, with some contextual modification. They have proved inescapable. They have been the basis of all subsequent progress, both in pure science and in technology. Now I have one last point before we leave the atomic theory. I've stressed repeatedly in previous classes that when you reach the fundamentals of some branch or area of physics, they're always expressed in the form of mathematics, of equations, often bristling with complex and advanced terminology and symbols. Now, I'm going to give you a really good visual form of that when I'm there in person on Saturday. That will stun you. But I just want to say here that this is eminently true of the atomic theory also, even though I ended my discussion of the theory on an earlier and more qualitative level. You still had a lot of math in what I gave you, but I didn't formulate the atomic theory as such in mathematical terms. But quantum mechanics in our century, if we can ignore the lunatic parts of it, has in essence taken the atomic theory all the way here, by providing and explaining the atomic behavior earlier observed in terms of the series of fundamental laws of atomic and subatomic behavior. Laws expressed in what else? In the form of mathematical equations. Now far be it from me, who quit in the 19th century, to even hint at these equations. I simply want to close by ensuring that you have at the forefront of your mind the fact that physics, here as elsewhere, culminates in mathematically stated fundamentals. And to emblazon this on your mind, I have printed in the handout only one such atomist equation, number 6, Schrodinger's famous wave equation. Just look at it. Now I have here an underscored, do not read to class, because I can't read it. But it happens to be the law, it's to state the law that determines, for instance, the nature of electron orbits in atoms. Now this equation takes us way outside the boundaries of these lectures and of my knowledge. So for my purposes, you don't have to understand the symbols. I just want you to gaze at them and be impressed before you glaze over. Now, of course, if you want to understand the equation, I suggest you take a course in quantum mechanics, but you must have Dave Harriman at your side. Protect you and distinguish the truth from the garbage which will emanate from the professor. You can ever arrange such a wonderful experience, go and do it. All right, that finishes our handout, and that finishes the atomic theory, and I want to take a few minutes now for a section entitled In Conclusion of Our Discussion of Science. The next 2 lectures are philosophy, so this concludes our discussion of induction in physics, a section entitled Inductive Errors. You know, when you give the right method of something, it's usually followed in conclusion by a statement of the wrong ways that you should avoid. So I want to discuss the main sources of error possible when you perform the process of induction. And actually, I'm following the standard Aristotle's procedure here. First, you give the positive forms of logic, and then you put the fallacies at the end. So first, let me give you a summary of 5 positive principles that you have to follow to claim true inductive knowledge. Now, I know that you're going to be tempted to take notes on this, but don't, because I've got them typed on a handout, which you will get either tomorrow or Saturday. So I'm just going to wait through it and just listen, because it would take me 10 minutes to wait for you to copy them all out. I should have thought of this, but I didn't. 5 principles or rules that you must follow to have a proper induction. 1. At every stage of science, valid concept formation is essential. If you want just a word right, concept formation. Because valid concepts are the only green light to valid induction. 2. Induction begins with self-evident, first-level gens, to which all other gens must ultimately be reduced. You can call that reduction to the first level. 3. Induction requires the contextual discovery of causal connection using the methods of difference and agreement. And that's the essence of experimentation. So you can call that one difference and agreement. 4. Induction at every stage beyond the first level requires integration with other knowledge, and on the highest levels requires the discovery of principles which integrate fundamentals from a diversity of fields. So you can just call that integration. And finally, in the physical sciences, after their early stages, the above steps depend on and are performed through and only through mathematics. Call that one math. Measurement, numbers. Now, I can't resist observing in passing, because it's key to induction, that every one of these rules has a counterpart in some form in the theory of concept formation as outlined in IOE. And just to run through it rapidly, it should be self-evident to you if you know that book. Well, is the rule of the essentiality of concept formation got a counterpart in a book on concept formation, obviously. And of the issue of valid concept formation. What about the reduction of all gens to first level gens? Well, what about the reduction of all concepts to first level concepts on the self-evident perceptual level? Cause and effect. What about the fact that concepts have to be defined in terms of essentials? And essentials are the causal characteristics that lead to the derivatives, their effects. And that this knowledge is also contextual in concept formation. Integration. Well, of course, the whole thing about definitions and higher concepts, concepts in the hierarchy is greater integration. And Ms. Rand stresses that all your concepts must be integrated into a unified system. And what about math? Here I'm treading on lecture 5. Just remember, the concepts are formed by measurement omission. That should give you a real, you should be able to write lecture 5 on that basis alone. Now let's turn to inductive errors. It's possible to make honest errors in applying any one of these rules. Errors which don't involve any philosophic corruption. But the fact is that so long as you know the proper principles explicitly and conscientiously seek to follow them, these errors will fairly quickly show up simply by the continued use of the proper method. And this is why science, by its nature, is self-corrective. For instance, overgeneralizations, in which a limitation to a specific context has been overlooked. are soon enough shown to have exceptions in some new context. And you know that Einstein is supposed to have shown that Newton holds only when you deal with speeds that don't approach the speed of light. If I dare say that Newton overgeneralized, which I hate to say, especially in favor of somebody in the 20th century. Or another type of example. An imperfect fit of theory to data is soon supplanted by a better theory. And in the process, an earlier formulated law may be amended. And a wonderful example here is Newton and Kepler. Newton used Kepler's third law to reach the law of gravitation, as we saw. And then, I didn't tell you this part, but using the law of gravitation, he turned around and corrected Kepler's formulation of the third law itself. That's actually true. Kepler had made a small mistake in formulating the law. Newton used the law to reach the law of gravity, and then using it, turned around and said, well, in effect, to the ghost of Kepler, you made a mistake here. This is what your law should have been. Now, that is a truly stunning example of science being self-corrective, because they all use the same inductive method. Further, innocent mistaken explanations, such as the fluid theory of heat, are quickly shown either to go beyond the data, or not to be the only possibility, and or not to be able to explain the known facts, and are eventually supplanted by truer ones. Now there's an exact parallel here to deduction, which is supposedly a form of reasoning which is not a problem. Nobody walks around holding their head in their hands and bewailing the problem of deduction. But it's an exact parallel here. You can honestly commit a fallacy in deduction. People do it all the time. But adherence to the rules of logic reveals it in due course. So where is the problem? Neither form of reason, induction or deduction, is infallible or automatically correct. But this doesn't mean skepticism, nor does it indicate any philosophical problem. There is no more a problem of induction than there's a problem of deduction. Now, judging from my own knowledge of the history of science, the major source of inductive error among uncorrupted scientists is premature integration. The attempt to explain observations before enough information has been gathered to make a rational explanation possible. And this is a very understandable error, because man has to be able to explain the world around him. So the seemingly inexplicable, even at too early a stage of knowledge, often provokes a rush to invalid answers. And one example here is Kepler, who discovered 3 valid laws of planetary motion, and then explained them on the basis of the theory that the sun was exerting a magnetic force on the planets, and thereby causing them to move in their orbit. Now, Kepler had some valid reasons for his theory. It wasn't wholly arbitrary. He was right, for instance, to note that we already have the example of a giant magnet, namely the Earth, acting to move smaller magnets like compasses. And that's what he took as his analogy. But his error was to decide that he could take the model of the Earth moving magnets and apply it to the sun. So it was integration on his part. It was intelligent, but it was premature integration. But since his work was part of the development of science, Newton, in short order, using the same rational inductive method which had led Kepler to his laws, Newton revealed the true nature of the attractive force the sun exerted on the planet, and thereby showed that Kepler's magnetic explanation was an error. Now let's turn to people or intellectuals at large, because the major sources of inductive error among these groups have nothing whatever to do with the kinds of mistakes that honest scientists make. The same general sources of error that produce popular or intellectual disaster in every form and field of thought do so in induction as well. And you can summarize the cause of our thought, people's thought being rife with errors in one simple statement. the absence of any defined method of induction, and the reliance instead on emotions and authorities. That is what creates the so-called problem of induction. People have no defined method, and they rely on emotions and authorities. There's actually no other way to explain such false and even absurd inductions as racist or rationalist generalizations, or ridiculous superstitions paraded as causal connection. You can't explain any of that except on the basis of hatred, desire, fear, etc., and or conformity, tradition, obedience, political decree. Typically, these mentalities make a pretense of having evidence, but it's the swan swine type of evidence. They merely enumerate some instances that allegedly justify the generalization. For instance, they count up or point to some Chinese people who run laundry, or some cases where walking under a stepladder has been followed by disaster, and then they immediately generalize without any method of philosophy at all. Maybe they despise the Chinese, or they fear the next unknown form of divine retribution through ladders, or simply because their parents have taught them that God prohibits walking under a stepladder. Now again, these emotionalist and or authoritarian types of epistemological corruption are in no way unique to induction. They can and do poison every form of thought. So the only thing to learn from it all, which should be obvious by now, is that induction is not validated simply by enumerating instances. Piling up examples without analysis is useless and proves nothing, because there are many cases where one instance is sufficient, as we've seen, and where millions are insufficient. For example, millions of men are actually immoral, but this has no tendency to prove the generalization that all men are so. Now let's leave the debased level of today's inducers and turn to the philosophical issues involved. My whole discussion of induction has rested on the philosophy of objectivism, in part on a valid metaphysics, one which recognizes the fact of existence with all its corollaries, including causality, and in part on a valid epistemology, which recognizes rational rules of concept formation and of objectivity. If, by contrast, you hold some version of mysticism or skepticism, or rationalism or empiricism, to use that terminology, then you may as well not enter the field of induction at all, because you are thereby cut off from reality at the outset by your own philosophy. This is obvious in the case of mysticism, which has been the enemy of science from day one. It's been extremely harmful, even in mysticism or intrinsicism, even in its most plausible form, which is rationalism, leaving aside, divine revelation. Because by insisting that scientific truths can be discovered by deduction from floating abstraction, what we get are results like Plato's inferring teleology. And you know what teleology, the idea that everything moves purposefully, destroyed science for centuries. Or you get the Greek rationalists inferring that planetary orbits must be circular because that's the perfect motion, etc. Because of this kind of rationalism, science was retarded for centuries. That's a form, the best form, of the intrinsicist or mystic viewpoint. Dave Harriman once observed to me how easy and rapid the progress was in electromagnetism as against astronomy and mechanics. And the reason is simple. The Bible has nothing whatever to say about electromagnetism. So scientists were free to follow the evidence. Imagine, by contrast, the disaster that would have ensued if the Bible had a dogma on the speed of light, or the influence of moving magnetic fields on electric circuits. We would still be living in a pre-industrial age. Thankfully, the Bible was written by such ignorant and primitive minds that the concepts of electromagnetism were not even grasped by them, let alone dogmatized about in the name of God. Today, however, the worst enemy of science is not the religionists, not any longer, but the skeptics. And I mean the professors and researchers in physics who proudly throw out reality and proudly embrace the arbitrary since nothing is knowable. In their view, their idea of science is simply to, quote, save the appearances, as they say, while abandoning any attempt to understand what is really going on in the physical world. Now you'll say to me, oh, you're going too far. Does any physicist really abandon the physical world? That's just too much to be believed. So this is my textbook that was used, I don't know, I hesitate to count how many years ago. Modern Physics by Van Name. It was used in university as a textbook. And I'll just read you a passage that I read as an undergraduate, and I thought, what a weird subject. He's presented Einstein, with all those paradoxes that a moving rod is really shortened and the clock is slowed down at a certain velocity. And then he writes this paragraph without blushing at all. Quote, the question might now be raised as to whether or not a moving rod is really shortened by its motion and a moving clock really slowed down. The answer, of course, is that motion has no effect on the properties of a measuring rod or clock. However, the real length of a rod plays no part in physical theory. Only measured quantities are of interest. Unquote. So, he doesn't care what the real length of the rod, that's nominal. No one can know the real length of a rod. You can just say that when you measure it, if it's going very fast, it measures differently. So that's it. Now, this mentality, many of them go so far as to deny outright even the existence of atoms, or anything which isn't a direct percept. For instance, the positivists are out-and-out empiricists, and they reject any conceptually reached knowledge of reality. So the method of all these skeptics is to come up with an arbitrary set of mathematical formulae, which they righteously say at the outset, these are uninterpreted, undefinable, and unvalidated. And that's actually true. I took a course in quantum mechanics, and the professor came in, I'll never forget this, and I'm not exaggerating. The professor came in and put a capital T on the board and a small t. And he intoned, to every capital T there's a small t. So, I just started the subject, I didn't know, and I raised my hand and I said, what does T stand for? And he looked at me indignantly and he said, these terms are uninterpreted at this stage. They have no meaning. And he gave us, 8 or 10 of these completely meaningless gibberish. You start with mathematical formulae, uninterpreted and unvalidated. And then you churn out mathematical manipulation until a miracle occurs, and it is on their premises. You can interpret your conclusions as predictions leading to actual observation. At which point, they say, the theories are confirmed, until the next percept comes by which conflicts with their theory, or doesn't fit in. At which point, they just throw up their hands and start to tinker again with their mathematical postulates. Now, I know you think I'm exaggerating, because nobody could be as bad, but that is because you are too benevolent. So I have to quote to you, late as it is, another statement. This one made my hair stand on end. It's from a professor of evolutionary genetics at the University of Leeds in England. And it was part of a book review, and I'm not going to give you the whole thing. It appeared in the New York Times on April 16, 2000. And he went off on to what he thought science is. Quote, personally, I like to think of the universe not as a machine. This breaks me up. Personally, I like to think of the universe not as a machine, but as a bus network, in which the identity of the buses and the reason they keep running are ultimately unknowable. Science is like a bus timetable. Forget truth. if you can put together a good timetable, you'll have a much better chance of catching a bus. Unquote. Now, he's not joking. This is a perfect example of save the appearances, ignore reality. You have, and you can have on this view, no idea what buses are or why they run as they do. You simply come up with an arbitrary hunch based on some samples that you arbitrarily declare are enough. And then you arbitrarily theorize and predict the bus's future comings and goings. And you cling to your formula until the buses start behaving differently for some unknowable reason, at which point you say, well, we were never interested in the real truth to begin with. So let's guess again. Science is ever changing. There are no absolute. Who can solve the problem of induction? Now, if you ask whether these people have any criterion at all by which to differentiate between two purely arbitrary theories, assuming both were able for the moment to save the appearances, they have one wholly absolute, and that is Occam's razor. Did we discuss that in this course? Well, Occam's razor, ain't she a non-multiplicanda sunt praeter necessitatem? I just had to say that. Entities are not to be multiplied beyond necessity. He was a medieval philosopher. And it's the principle that in evaluating competing theories, the simplest one is the right one. In other words, the one that invokes the fewest number of elements or complexities. So the criterion of validation is not correspondence to reality, but paucity of constituents in your theory. These people, for instance, accept Copernicus over Ptolemy. If you ask them why, they say, well, both theories could be true, but Copernicus uses fewer postulates than Ptolemy to predict the same observation. Copernicus, for instance, doesn't need epicycles, so he gets 1 point for that. And they add it all up. He's got a simpler theory. He wins. Now, Occam's razor is Occam is O-C-C-A-M. Occam's razor is an utterly invalid criterion by which to judge a theory. Simplicity designates the number of elements in the theory, and it is totally invalid to distinguish epistemologically between two theories according to the number of elements they hypothesize. If a certain element is a fact of reality, as proven by the proper inductive method, then it must be included in a valid theory, even if another theory ignoring it saves the appearances. If you're most generous, you could interpret Occam's razor as a misguided way of saying don't be arbitrary. But it is misguided and harmful. And by Occam's method, people have actually rejected reality itself on the grounds that such a metaphysical notion needlessly complicates the mathematical equations, which by themselves, without reference to reality, save the appearance. So reality is thrown out as not simple enough. Now the truth is that explanations must be true and not merely simple. I mean, here's an easy common sense example. A very complex set of clues condemning one murderer as against a simple theory condemning another. Do you say the simple one is automatically the true one? That's ridiculous. Now, I think Occam's razor is a real danger to science. It is characteristically used to cut science's throat, and it's typical of the perceptual level mentality of skeptics who are now retrogressing in physics to the intellectual level of savages. What physical science needs is to return to reality by following the rules of induction which we've developed through studying the actual methods of the great scientists of the past. And I trust you now understand something about these methods, at least in essentials, and should now, if I've calculated correctly, you should now be eager to see how all of these methods and principles apply to philosophy, and how they're used to validate philosophic induction and philosophic laws. And that is the topic that we turn to next time, in a shorter lecture. Thank you very much. Now again, it is hopelessly late. So I'm going to allot 7 minutes for questions. And someone submitted a written question. So while you're getting up, some written questions, as a matter of fact, more than one. So while you're getting up to the stand, I'll take one of these. And to condense it, he says it's not always self-evident that a generalization is first level. I'm worried that I might fool myself into accepting a generalization as first level when it really needs to be reduced. What's the answer? There can be no criterion as to defining the self-evident as self-evident beyond its available to perception. If I say to you, how do you know it's self-evident that an apple is there when you look at the apple? You see it. There's no more you can say to be sure you haven't fooled yourself into thinking it's a deduction from something else. Once it's perceptual, that's the answer. The same is true with first-level concepts. How do you know the table can't be reduced to something else? You directly see tables and their differences from chairs. Once it's perceptual, you can't fool yourself into thinking it's perceptual, but it's really hard. That's what the self-evident means. Now, this same gentleman, I'm trying to find something of general. All right, before I go on with him, let me take a live question there. Yes.
Hi. In your explanation of the development... Oh, sorry. This is Jason Crawford. In the history of the atomic theory, it seemed that scientists were using the atomic theory to try to explain things before it was finally confirmed, when it was still just even in the possible stage. How is this legitimate, and how do you distinguish this from the positivist notion that we just have these models that we use and they're useful whether or not they correspond to reality?
Well, how is it justified for advocates of atomism to use it to explain things before it was proved? Isn't this using the arbitrary to reach a conclusion? No, it's certainly not, because they did not begin to explore its potential uses as explanation until there was evidence in favor of it. Now, once there was enough evidence to make it a possibility, then they were legitimately interested in saying, well, if this were true, how would it explain this? And if this were true, how would it explain that? In other words, it became a hypothesis worth following up. And what made it not arbitrary is that they identified at each stage. When each time they got a bit more evidence, well, that's more, but it depends on such and such. Do we have any evidence for such and such? They were very scrupulous throughout in never pursuing the arbitrary and always identifying the status of the evidence available to them. Can I take the next question? What's your name?
My name is Phil Eklund. I'm having a little bit of trouble understanding how a math or a calculus, which is derived from continuously variable or divisible variables, can validate discrete phenomena such as atomism or quanti or the atomic orbits.
Dave, you want to take that one, being more of a math expert?
I'll talk to you about it afterwards. How's that?
Yes, next.
Hi, my name's Tom Wheeler, and in the very first lecture, you gave a razor which you did not give a name to. It said generalizations are not to be multiplied beyond necessity. Doesn't that suffer from the same weakness that Occam's razor does?
No, because I went on to say what makes them necessary. The question was, if I say generalization is not to be multiplied beyond necessity, is not the same weakness as Occam. I did not make simplicity the criterion. I said there has to be a basis in reality, and I defined what I meant by that. A context, first level gens, step-by-step progression up a hierarchy by definite methods. I was saying you cannot assert arbitrarily. That is not the same thing as saying count the elements And if someone can explain something by 3 gens, that's better than by 5. So you're equivocating. All razors say something shouldn't be multiplied beyond necessity. But the difference is whether they define a context for what is necessary. Occam defined no context except quantity. Ayn Rand has the concept, concepts are not to be multiplied beyond necessity. That's one of the razors that she calls Rand's razor. So not all razors are arbitrary the way Occam's is. I just didn't. I haven't got the time to do it again. I want to work one more question in. Yes, last question.
Hi, my name is David Peng. I hope this question isn't too
David?
Yes.
Yeah.
I hope it's not too much of a tangent, but I was hoping you can comment on this modern science education, particularly at the college level. You mentioned before learning things from textbooks, and is that necessarily bad or not?
Well, it's okay to learn from textbooks. Is it okay to learn from modern textbooks? Is it possible to learn from modern textbooks? It's okay to learn from them if you can separate out the true from the false. It's extraordinarily difficult to do this in physics if you don't know physics. You have to try to separate out what part is first-handed, what part is based on observation, and what part is somebody's arbitrary theory. That is extremely difficult to do. The only real way to do it is to do it the way Dave Harriman does. Go back and develop the history of physics hierarchically, as it actually progressed. And you then have a test by which to determine whether your text is any good or not. But by that point, you already know physics, and you will laugh at the text. Now, the great hope here is that Dave himself is actually preparing a curriculum of physics based on the historical hierarchical method. And when that's available, you can forget about the text, and that will give you the essential development. Now, if you're a physics major, you have to know the details of the text, but at least it will give you the line to follow. And thereafter, you learn in reverse. Ayn Rand used to say to me, your classes are not a total waste in philosophy, because learn in reverse. Keep asking yourself, what is wrong with what this guy is saying? And, it's a painful way to learn, but it's still possible. So when your physics professor gets up and says he's got a bed full of wavicles, try and figure out what's wrong with what he's saying and what contradictions there are, and look up and see what alternatives there might be. It's a grueling task. I grant you that. You have to be extremely wary, particularly in physics, because they take the worst nonsense and give it mathematical formulas. And the result is you're totally intimidated into thinking, well, nobody would write junk and with all those symbols. But unfortunately, they do, and that is the word today. So I can't tell you how to work your way through the thicket and separate the good from the bad. And as a matter of fact, I agreed with Dave only to go through the 19th century, because the 20th is such a mixture that I didn't want to enter it, certainly not from the point of view of finding out about proper methodology. I wish I could tell you more, but with that, we'll have to take a break until tomorrow. Thank you very much.